Hey everyone, how's it going? Hopefully we got some viewers after Comment's long stream. It was a good one though, so yeah, it was good. All right, so because we're starting a bit late, I wanted to I think we'll skip Sonic for this stream. What we'll do is talk about Scott encoding. I really wanted to get to do some Codewars. I wanted to try it out. A couple of people have been asking me about Codewars, so decided that I should probably do it. And I've had a look through some of the exercises. And I've got a little list here of things that I wanted to go through, and I was looking through it, and I think the one that's most exciting to me is, oh hey, how's it going, John? The most exciting for me would be, I think, Scott encoding. It's just like it's a really good topic, and I think everyone basically should know it, no matter what language you work with. If you are committed to the idea of functional programming, you should know about Scott encoding. So I want to talk about that a little bit. I don't know what's happened here. So I want to talk about it a little bit. Scott encoding you might know as you might know of something called church encoding. And Scott encoding is very related, just slightly different. I don't know why I'm not able to load up my my collection here. Let me have a go at this. So Scott encoding is related, and there's a paper here called Church Encoding of Data Types Considered Harmful for Implementations. And if you read this, you can actually there's some good comparisons down below. So if you are familiar with with Church encoding, Scott encoding is just slightly a bit different, and you can go through and have a look. Thanks, Commit, for the raid. Sorry, Commit raiding me meant that I was listening to my own stream, so that was a problem. Okay, so if you look down in this paper, you can see, yeah, so there's list in Scott encoding. So this is a comparison. There is, up here, there is, I think, list in church encoding. Oh no, that's piano numbers, lists. Here we go, lists. So lists in church encoding, this is what they look like. So if you're familiar with church encoding, you don't have to be. We'll go through a heap. I mean, this is basically what the exercise is, to go through and practice encodings. So if you don't know church encoding, don't worry about it. But you can see, if you do know church encoding, you can see it looks like this. This is the church encoding of a list, and that might look a little bit weird. It is a bit weird. Or what we could do is go through and do something called a Scott encoding, and this is what the Scott encoding version looks like. So this is obviously a lot nicer. If you look at this and you compare it to this other example, you definitely want the church you want the Scott encoding version. You want to skip the church version. So you should look at this. And the thing is, what yeah, we'll go through what Scott encoding actually is. But if you're familiar with church encoding, think of it as just basically like a slightly better version of encoding things. So yeah, you don't have to worry about it. We'll go through what Scott encoding actually means. That's just if you're familiar with church encoding. So Scott encoding is the idea of taking an algebraic data type and encoding it in terms of functions. So you can take any algebraic data type and encode it using just functions instead. And so we'll go through and we'll practice a heap of these. I think that's what this is going to do. It's going to get us to practice a heap of these. But basically, you can think of any type of data type. So you can have like, let's open up a Haskell file. We'll call it scot.hs. Whoops. Sure. Thanks for the follow, Justin. There we go. Let's load up this. Sorry, it makes this take a little bit. Here we go. All right. So let's say booleans. Actually, let's go something like either. We'll call it. We'll have either. So we'll call either prime. Takes two type parameters, a and b, and we'll either have left prime or we'll have right prime. So this is a data type we've just defined. Let me load it up in GHCI just to show you that it works. There we go. And what we can do is, instead of writing it like this, so what we've done is we've created two constructors for this type. Instead, what we could do is do something called Scott encoding. Or often people refer to it as church encoding. Church encoding and Scott encoding are slightly different, like I was pointing out with that paper. They're slightly different, but we're a bit relaxed sometimes, and sometimes we say it's church encoding. But if you want to refer to it more properly, call it Scott Encoding. And for a lot of data types, church encoding and Scott encoding are the same, so they won't really matter, but I think for either is actually the case where it doesn't actually matter. But you can actually encode this as a function. So instead of having, we can encode the same amount of information as a function. So here we've got something called either, and it's got two constructors. Sorry, there we go. I'll fix the data type there. So we had either, which has got a left or it's got a right. And what we could do is either prime prime. And we can actually encode this as a function. And so here I'm actually saying type, which is a type alias. So up here we've actually defined a data type that's got two constructors. Down here we're going to define something that's got 0 constructors. The only constructors are function constructors. So we're just going to encode this data type using functions. And what we'll have to do is we'll have to do a little bit here. We'll have to say for all C, A implies C, B implies C, and we get a C. And we'll have to enable an extension. Thanks Ben for the follow. It's good to see you in here. That's good. Hopefully the lab is going well. So here what we've done, we've got this constructor here left, and we've got this constructor here right, and we've got this data type either prime. What we could do is encode it as a function instead. And so what we're saying is that if we can take A to a C, or we can take B to a C, then we can get a C. So this is just a way of saying if you give me a way of taking an A to a C or a B to a C, then we can get back a C. And so the constructors now look like, so now we can say left takes an A to an either prime prime A B. So left can be now a function. What's it look like? It takes the left and it takes the right, and we get back a C. So let's use whole driven development to come up with the implementation of this. Oh, sorry, we got an A there. Let's start like this. Let's start like this. So it's going to say, we've just put a hole here. So we've got this A, which is like our actual value. So we're implementing we're writing a binding that represents these constructors. So up here we had a constructor. Here we've gotten rid of the constructors, and so we're kind of trying to recover them. So here we're going to use a function to try and recover this constructor up here. And so we're running a function. Let's just say it takes an A, and now we have to get back this either thing, this thing that we've defined up here. And what I've done is done the Scott encoding. We'll practice that a bit more so that you can I don't know, learn how to do it yourself, I guess. We'll practice that quite a bit more. But yes, here we're trying to recover the constructor. And so this constructor here, what we've done is put in a hole to say, what do I need to return here? What do I need to return for this either? And that's actually expanded the type alias. And so now what it says is I need to give back a function. And so it's got these two things inside of it. So I'm going to just extract these out. So L and R. So now what we have in scope is these three things, and we need to return a C. How can we get to a C based on what we have in scope? Well, we've got an A, and we have an A to C. So if we just apply L with A, there we go, it compiles, and we've got this R in scope, which we don't need. And that R actually represents the right-hand side, so we can actually take this and implement right, get rid of that. And this will be a B. So I'll change the name over. There we go. So now what we've done is we've represented the same amount of data. So this is either, which has got two constructors left and right. And what we've done is we've represented exactly this, but using functions instead. So now all we have is a function. And you might notice that we've got this for all C in here. We do need to have rank n types to be able to do this. In Java, you can actually use method level generics to be able to represent it. So you can actually do this in Java as well. So even though Java doesn't have the idea of algebraic data types in terms of syntactic, it doesn't actually syntactically have the idea of having multiple cases except for its enums. We can actually represent it instead using functions. So functional programming actually lets us retrieve back algebraic data types. And so often the criticism of Java is, oh, it's got no algebraic data types. It does have algebraic data types. You just have to use this Scott encoding to retrieve it. And it's completely fine. It's just a very mechanical thing to do. There's no actual problem with Java. Like if you gave me a list of problems with Java, this would be at the bottom. It doesn't matter that Java doesn't have syntactic recognition of algebraic data types. We can still retrieve either. And maybe we should do that. Maybe we should make an either.java. I'll show you what that looks like. Okay, I don't know why I have this file in my temp directory, but that is not good. Do not do that. You think this Scott encoding is a performance problem is another way to close the algebraic data type in Java. Interesting. What do you mean by that? I'm guessing that's Tony behind QFPL. Thanks for the follow, Kraken. So we're gonna have this. We'll write this as an interface. Is that right? We want it as an interface, either A, B, and then we want to have C. We'll call this fold. I think this is what we want. Sorry, my Java is not, I mean, I know Java pretty well, but it takes me a little bit to get used to the syntax every time. So what we could do is have function from A to C. We'll call that L. So this is similar to what we had here. Call that L, and function. Yeah, I'm sorry about the dog. Is this what we want? Let's see if we can compile this. Identifier expected. Where did I miss identifier? Ah, is it like that? I think I've got the things flipped over there. It needs to be like that, am I? Oh, I always get the order mixed up. It might be like that. Okay, it needs to import. Was it java.function.function? I can't even remember this. Using a function to encode the ADT encodes at least a stack frame. The goal of the ADT is to ensure that there are a finite number of data constructors. This can be achieved in Java by taking advantage of a couple of language tricks. Yes, -Brisbane. This can be achieved by Java by taking... Okay, if you let me know the language tricks, let's go through it. Util. So here we go. This is a representation of this, basically. It's roughly the equivalent. So here we've got a function, and then here we've got the Java version. And so we could actually implement, what is it, static. Getting somewhere with this, and it needs to return either A, B, okay, yep. And then we need this fold. No, we need to return L of A. I think I need to apply, is it? Have we gotten somewhere? Yes, okay, cool. So that's the left constructor, and then we can change it over to, let's change left to right. And this will be a B now. Here we go. Type yeah, this is actually I think we wrote some Java last week, didn't we? That's a problem. Okay, so this is a way of encoding encoding either in Java without using enums, without using partial functions or anything. This is just total functional programming in Java, and so we can recover either based on the fact that we can Scott encode something. And so we've just Scott encoded and then written down an interface. So you can take data types, break them down into interfaces, and then just combine them together. Now, QFPL has something for me to look at. A class with a single private constructor cannot be subclassed. Okay. You can write an abstract class either with a single private constructor, then two subclasses that are nested. This ensures there's only two constructors, and there's only one. So there's any value of type either is either left or right, and definitely not anything else. Right, okay. Okay. Yes. Oh, yeah, it's definitely noisy. Okay, and so you're saying, so I think QFPL is saying that is more efficient for us to do it if we know that there's only 2 constructors. Are you saying that we could use instance of instead? Yeah, okay. So even though, but I mean, Java's not going to give us any... I mean, sure, you can scribble it up, we'll have a look. I mean, we're gonna, yeah, I mean, that's, yeah, the most efficient way to do it in Java is kind of not really the point of the stream, but I would like to see that anyway, so yeah, that'll be good. The point is, we can encode everything. Yeah, instance of will be used, okay, so it's a little bit dodgy, but okay, sure. This is not dodgy at all, it's just probably a little, not very performant, but, you know, whatever. That's Java. Cool. So it is possible for us to do this in Java. We can just break down everything into interfaces. We have to have this idea of rank n types, as some languages can't do it, but a lot of languages can. If you have no types at all, you can still do this. So yes, take advantage of Scott encoding. I've done it in JavaScript. It works. It's not great, but it works. Cool. All right, so let's get some more practice with Scott encoding. That was just an example of us. I was just trying to show that we can do it in different languages. Don't have to do it in Haskell. We do need a little bit of a language feature to be able to do it. Even Java's got that, so it's not a huge bar, but we can do it. Cool. So let's get some more practice with it. Let's see if we can click this train button and get this thing going. I don't know how well. Yeah, this doesn't look like it's going to work very well. Let me make it a bit smaller. Here we go. All right. So let's look at the exercises. I'm going to have to probably copy and paste this into Emacs or something so I can work on it. Let me just get rid of this. There we go. Cool. Now we've got everything here. So here's just a heap of exercises, and they have Scott encoded a lot of things for us. I'm just going to format it slightly differently, just to make it easier for me to quickly look at. Okay, so they've got Scott encoded maybe, Scott encoded either, and Scott. So they've done the Scott encoding for us, and so we just have to derive the functions from it. So you can see this is Scott encoded maybe. One way to like derive the Scott encoding is to look at like a fold over the data structure. So if you have what we had before, so we had either. So if you look at the fold function for either, so fold for either would look like. It actually looks like either. Let me look that up in Google. So there's a function called either. Here we go. So this is a function for either. So basically, if you look at the fold of any data structure, you can recover the Scott encoding for it, basically. So here we have either A and B. So this represents the left. If we take the left, take the value from the left, which has got an A, to a C, or we take the value from the right, which has got a B to C, then we get back a C. So this is the fold for either. You can look at fold for list. You can look at fold, which is fold right, like we went through with Data 61 course. We went through that's fold right. Either we've got maybe. So maybe has got a type called maybe as well. So this is a bit of convention in Haskell to call the fold function after the data type. So here we've got maybe. It has the nothing case, which is just return B. So you could actually replace this with Eunuch to B, and that would be, I don't know, you could kind of maybe see the similarities between either and yeah, the either's fold, and maybe if you replace this B here with like Eunuch to B, basically means that you can get a B, which this represents the nothing case, and then this one which represents the just case. So you can get a B from a maybe. So if you just write the fold, which is just a way of taking the constructors and replacing them with, replacing them with a function that computes a different type, then you can come up with the Scott encoding. So here we got the one for maybe. So this represents the maybe function. Look at it, it looks exactly the same. A to B, B here, maybe A. You just drop the maybe. Same with list. And then we've got either. This is one that we just did. We had a bit of practice on, and then we've got pairs. So we've been practicing so far on, like the ones that we've talked about so far are kind of like algebraic, like sum types. So ones that you got multiple cases. Where for pair, we have just 2 values. And so instead of having 2 things being passed in here, we just have one function which represents, so it's got A and B, give me a C, then we can get back a C. So if you can give me an A and a B, then I can give you a C. And that's the Scott encoding for a pair. So let's have a go at implementing the functions here. So we've got a pair A and B. So remember this is a function, so we'll have to unpack it and we'll get a function out. Let me reload this. Let's use type-driven development, put in a hole here, and we'll say to do, and we need to return an A, B, and what do we have in scope? Well, we've got this thing. Okay, so we've got this function, and it's got a for all C, so that means we get to choose what the C is. I want the C to be this. I want the C to be A and B. So, let's copy and paste this over, and we'll copy paste it over here, and we need to substitute C for A and B. So we've instantiated the C to be A and B. What can we do to get this function? How can we get from an A and B here to an A comma B? Like, this is the constructor for tuples. Well, if we look at this function, look at this. It's exactly the same. So this is just the tuple constructor. So we can construct tuples by applying 1 and 2. We get back the tuple 1, 2. And so it's got exactly the right type. So if we were to run f, but give it our function comma, this should work. Yep, there we go. So we've just given f, so we've taken this A and B to an A and B. So this comma here is just making an A and B together. And so we've just recovered, we've taken this S pair, which is the Scott encoding, and we've just recovered the actual tuple. So we can convert in one direction. We can go from an S pair to a tuple. Now the next exercise is to go the other way. How can we go from a tuple of A and B to, whoops, what did I do there? A and B to a tuple to our Scott encoded version. So we'll put in, we know that we're going to have to construct it, so we've got this S pair, we'll put in to do here, and what do we have to fill in? We have to fill in a way of taking a function to a C. If I give you a function from A, B to C, then you'll give me back a C. So let's make a lambda for that. So we've got this function in here, put another hole. So, I mean, I knew that I had to return a function here, right? I know that to do was a function. So that's why I put a lambda in there. Now we've got an F. Now we've got this F in scope. We have an B and we have an A. And look, we need to return a C. And look at what we've got in scope. We've got exactly the right stuff to be able to return a C. So that goes F, A, B. Whoops. Reload. Cool. So now we can go from a Scott encoded pair to a tuple, and from a tuple to a Scott encoded pair. Anybody confused by how Scott encoding works? Does Java have high kind of types yet? No, it does not. Definitely not. Scala does, but kind of. So there are. I mean, if you have to use Java, don't, and use this instead. I've been working on this quite a bit. And it's very good. Eater is super cool. I've got it all built inside of Nix, and I can actually build. Let me show you this. I can do this. So I've got the pure script compiler running on the JVM. Super slick. Super slick. I'm getting messaged probably by Queensland people. No. Yep, super slick. Anyway, pure script running on the JVM, super cool. So don't use Java. A fold will be church encoding. Yeah, you're right. Yeah, fold will be in church encoding. Yeah. Yeah, and we're focusing on Scott encoding, which is, yeah, it's, I mean, for a lot of data types they're actually the same, but yeah, that's right. Okay, so let's write the function first based on, well, there we go. Cool, we got a link from Tony. All right, let me see if I can bring this up. So we got a link. It is, okay, so you got an abstract class either, private constructor on the either, but public final class for each case, and then a fold which just does an instance of, right? So the point here is that this will be more performant than the version I wrote. Even though this is slightly unsafe because there's some casting going on. but you write this once and you can just keep reusing it. So if you're after performance when you encode your data types as functions, then in Java, then this will be the way to go. Yeah, that's a good point. Thanks for showing that. I think I've seen this before, so yeah, I recognize it. This is a bit dodgy, but you know, you write it once, so all right. I can be convinced to do that. All right, so let's keep writing some functions based on this one. So we're based on this this S pair. So we're based on the Scott encoded pair. So we've got this F. I'm just pattern matching because I know that we've got a constructor around this function. So put in a to-do hole. We've got return an A. What we have in scope is just this F. So we're gonna have to use this F in scope somehow. So F to do. I know that we have to use the F because that's all we've got in scope. So put in a to do here, and now what we have is we have to have a function that goes A, B to A. Does anybody know? Does anybody remember what function? We did this a while ago during the Data 61 course. There was a function that looked exactly like this. Does anybody remember it? So we're taking this function and we have to use it. So I've just put in a hole where we have to supply something. We have to supply a function that takes an A, B, and gives us back an A. There is actually a common function that we use quite a few times in the Data 61 course for that one. Funny how this is an optimization you do in Java, yet the codensity optimization in Haskell is basically the opposite. A concrete tree turns into for-like function. Interesting. Yeah, that's a good observation. I like that. Codensity is basically the opposite. Yeah, that's a good point. Thanks, Viking for that. That is const. You've got it right. That is definitely const. Awesome. Good job. So that was const. ABA, exactly what we wanted. Awesome. Thanks for the follow, Twitch. Okay, S pair F. So this is going to be similar. Who wants to guess what the implementation of this one will be? Now we've got an A, B, B. Does anybody remember? Well, I think we did talk about this a little bit in Data 61 course. There is a way to derive this. There's a couple of ways to write this, I think. Const applied const. Yeah, okay. I think Haskell will have trouble inferring that. So I'll skip that. So there's flip const. There's flip const. Or there is const ID, I think will be the same thing. Yeah, here we go. So these, I mean, you'll have to alpha rename them, just substitute the names around a little bit, but here we've got B, C to C, and B, A to A. Either of these you can choose. We'll choose const ID. There we go. Cool, so now let's go swap. We've got an S pair to an S pair, and we're just swapping these around. So how can we do this? Let's deconstruct the pair. I know that I have to do that. Again, I'm guessing I'm going to have to use F because that's all I've got in scope, so let's go F. Okay, so we need to have an A, B to an S pair, BA. What can we do with that? How can we create that? Actually, another way to do it is, I didn't realize that we are returning an S pair, so here when I had this hole, I have to return an S pair, and I said, well, let's just use F because that's all I've got in scope, but how about that? If we construct an S pair, now we have to give it a B, A, C to C. And what we have is this. So this is looking interesting, isn't it? This channel does have ProFunctorBot. It is LambdaBot, yeah. I've called it ProFunctorBot just because the name was reserved. There you go, there's ProFunctorBot talking to you. Okay, so we've got this function B, A, C to C, and what we have in scope. So this is, notice how we could kind of make this work. So let's bring this stuff into scope. BA to do. Just a second, my cat has spewed up on my laptop, so I'll have to clean it up. I'm going to take a tiny break to clean up the spew that my cat just left on my laptop. Hang on. Alright. My kitten got, I got it fixed up the other day, so, I mean, that's, yeah, she's just spewing up, I guess, from the medication or something. I'll check her out later. I think she's fine. Okay. Where were we? Yes, I was introducing B and A into this because it was a lambda. I think, oh, did I make a mistake there? I did. Where did I make the mistake? What have I done here? Need to replace to do, oh. It needs to take the, it takes the function, takes another function. Is that right? There we go. So now what we have in scope. We have F, and we have F prime. We need to get back a C, and so the way we can get a C is by supplying B and A here, or here. And so what we've got here is F. So what we can do is supply it here, swap it around. So let's go F. Now it might make it a little bit easier. So here we've got A, B to C, and what we have in scope is a B, A, C. So what can we do with F prime to fill in here? There's something we can do with F prime to fill it in here. Any ideas with that? F prime is type B, A to C, and what we need is an A, B, C. What can we do? We can flip, exactly, flip F prime, is that right? Flip F prime. There we go, awesome, good job. So let's get rid of this. I'm going to refactor this slightly. I'm just going to notice some things. I noticed that we've got this F prime over on the right hand side and we've got F prime over here. What we can do is change this to function composition. So f.compose flip. So that's just a mechanical transformation you can do. If you get good enough with Haskell, you can just notice those things and then write f.flip. Awesome. So the way to swap a pair when it's Scott encoded is to just flip it, just replace it with just compose in the flip function. Super cool. All right, curry. What does curry do? Curry takes a pair of A and B to C to a function that takes an A and a B to a C. So S. Well, that is not an S pair. This is a function, isn't it? And then we have A, B. So one thing I've noticed here is that there's parentheses here, so we can drop those. That is equivalent. When you see parentheses on the right hand side for a function, you just get rid of them. So that's equivalent, that's exactly the same thing. This might make it more clear of the intention, but you can always just drop them. So I think that's fine. Cool, so we've got this function, and what can we do? We need to have, we've got this function f, which takes a pair of A and B to C, and we need to return a C. So we obviously need to use this function in some way. So there we go, yes, let's use this function. Now we need to give it an S pair of A and B, and we have an A in scope and we have a B in scope. So how can we construct an S pair? We kind of did it before. Let's construct an S pair. Now I need to give it a function from A to B to C1. We get back a C1. What is the C that we want? I guess it's for all C, isn't it? Yeah, we're constructing it, so it's all for all C. Alright, so we get given an F prime. So now here's the C1, so we need to create a C1, and what do we have? We've got F prime, which takes an A and a B to a C1. So we can just use F prime, A, B. But there we go. So that's constructing a S pair. And we're just passing this function around. So I'm just using type-driven development to come up with the solutions here. So we've got this function here which needs an S pair, and so we've given it an S pair, and that's how we construct it. So an S pair takes a function, and we just give it the two arguments that we've been given up here. Alright, so uncurry, so we've got an F, and again we can drop the parentheses from this side. We've got an F and G. Actually, let's unpack this. S pair, F prime. Just unwrapping it, so we need to return a C, and what we have is, we've got F, which takes an A and a B to a C. And then we've got this F prime. So actually, so we could keep going. Let's do it like this. What we could use is probably just reuse these functions up here. We've got first and second. We could probably just do F of, what would it be? Here. What we could do is, if we had this as an S pair, we could say F of first S, second S. That's a really simple solution, but that doesn't really teach us much. It doesn't really practice Scott encoding, although we could just do that. Let's do it. Let's leave that as the answer, but we'll practice the other version as well. What do we want to do? So we've got an F, S pair, F prime. So we need to give it, whoops, what have I done here? Oh yeah, it needs to have an A and a B. But what would be more interesting is if we could do it instead of like that. Yes, what would be more interesting is if we did it more like this. Sorry, use the F prime from the pair to do it. How's it going, Peppermint? How's it going? We are practicing Scott encoding. There's an exercise on Codewars that we're doing, which is about Scott encoding. I thought it looked interesting, so we're going to have a go at it. What would be more interesting is if we did this F prime from the pair instead. So instead of using this function, which was what we did here, which is just, it's decoding the pair here and it's decoding the pair here. Instead of doing it like that, what we could do is use this F prime instead. So instead of using F and then getting the things out, we could actually just kind of decode the function and then figure out a way to use this F. Should be able to do it like this. I'm not 100% confident, but I think we should be able to do it like this. So I've got this F prime that we're using, right? Yes, we're using F prime. So what we have in scope, what I need to give is an A and a B to C. A and a B to C. And look what we've got here. We've got exactly that. So here's another way of writing it. I actually like that solution better. That's a lot nicer. If we just fold the pair with our function, that's it. So this is kind of basically like uncurry is basically just creating as a function. Awesome. So that is pairs. We've done tuples, we've done pairs. Next exercises are about maybe. So we've done the one where we've got a product type, and now we're going to practice Scott encoding over a sum type. And so the sum type, notice how the product type is just a function that takes in many different values, whereas a sum type is just one that's got it's a function that has a parameter for each constructor in the data type. So you've got B, which is the nothing version, and then you've got here, which is the just. So you've got the two cases as parameters to the function. So pair is just a function that takes in multiple arguments, and the sum types are ones where you actually have you've got multiple cases for the function. Okay, so S maybe, let's deconstruct this. I think that's what we have to do. What is this function that we're implementing? It is to maybe. So we have an S maybe, and we need to implement a maybe. Alright, so what we have in scope is F takes a B, A to B to a B, and we need to return a maybe A. So I'm going to say this B is going to be maybe A. So F. So now we've got two holes because we have to give F two parameters, one for each case. This is going to be the nothing case, and so we need to take an A to maybe A. This will be the nothing case and nothing. And this one will be the just case, so we need to take an A to a maybe A. And how do we do that? We just use just. We just use just. Cool. So hole-driven development getting us to the solution there. From maybe. So now let's go in the other direction. So we have a maybe, and we need to return an S maybe. So let me construct an S maybe. Okay, so we need to return. So I need to give this now a function from B, A to B, to a B. Alright, so now we need to return a B, and what we have in scope is a maybe A. We have a B, and we have this function from A to B. So what we should do is deconstruct this M here. What we're doing is going to deconstruct this M, and say if it's nothing, then do one case. If it's something, then do the other case. Like do this just case. And like I said before, I don't know if this is in scope. Oh, it is in scope. There we go. So let's just use maybe. Instead of deconstructing, we could do, let's do it both ways. I'll show how I'll do it both ways. So let's do case M of nothing, then we get B. Let me put in holes for each one. We'll go through this really slow. Let's go yep. Okay, so now we've got two holes. We've got this hole underscore A, we need to return back a B. What do we have in scope? Well, we've got this function from A to B, and we've got a B. And so the only thing we can fit in here is this B. Like, there's no way for us to get a B from here because we don't have an A. So the only thing we can do is return B here. And that makes sense because this first case is meant to represent the empty case. Second one is, oh, look what we've got here. We've got an A, which has got type A. Now we've got a function A to B, so we could actually supply this A to this F to get a B. So this is slightly different from what we did above. We can just go FA. And there we go. That will compile and that works. And so we could do this. We could do pattern matching and pattern match on the maybe. I dislike pattern matching a lot. I don't think you should really ever do pattern matching. And so I would write instead like that, which is using the maybe. So it's using the fold over the data type. So we're folding over maybe and supplying the same arguments. And so because we've basically represented, because Scott encoding is basically the fold for the function, we can just say basically this is the fold. There's a little bit of like, changing arguments around in that, but it's basically the same thing as saying that the fold, the implementation for the Scott encoder maybe is just using the maybe function, which is the fold for this data type. So because someone's already done the pattern matching, extracted it out into a function, we can just use that function. Easy. So S maybe F. Need to return a boolean. So to do needs to be a bool, and what we have is an F. So let's use this F. I dislike pattern matching because that patterns don't compose. That's kind of the big reason why I don't like pattern matching. Patterns don't compose together. You can kind of nest patterns, but I wouldn't say that's composition. So I think functions compose a lot better than what like this maybe thing. I can just add more things in here. I can say maybe, and I can compose it with something else. Or if I had like a list of maybes, I could compose the two folds together and get a new fold. And that's a useful thing to do. If I had two patterns, I'd have to start nesting them, and that becomes like a manual thing to do. It's not something that is just composition, where you just put in a dot and you get it for free. When we have patterns, we have to actually, manually kind of put them together. There's no good compositional pattern matching. The closest thing that you get is something called lens, which is basically representing pattern matching as functions. And so if you were to represent pattern matching as functions, which is just folds, just fold functions, but lens goes a little bit further and does a really good job of representing the idea of folds as functions. And so you got the idea of like prism, for example, and these compose together extremely well. And so I pretty much never write pattern matching, and instead I either write just a function or I use lens if I need something that's a little bit more tedious than just, if I'm trying to use a function that's a bit tedious, I'll use lens, and lens removes all tedious stuff from writing folds and stuff. Hopefully that answers the question. Patterns don't compose as well as functions do, so I prefer functions. Is there a context in which using pattern matching would be better, or do you just generally avoid it completely? There are contexts where I do pattern matching, yeah. I try and generally avoid it. I'm not always successful in avoiding it completely, but I do generally avoid it. There are cases where basically, I mean, there's a couple of cases. One of them is to implement lenses and prisms and that. To implement them, you have to write the pattern matching, and then you've got them. It's kind of converting the pattern matching into a function. That's one case. Obviously, you have to write the pattern at first to be able to get the function that is more composable. The second thing is like total. When you want to ensure totality of things, using prisms and using lenses is kind of tricky. Composing together functions and to get like to ensure that you've totally matched all different possibilities of the input, that's really difficult. And so in those cases, I use pattern matching, where I need to ensure totality of things. I need to ensure that I've covered every single possibility. Yeah, I use patterns for that. I wish there was a way of ensuring totality with lenses better. There's no good answer for me yet. I feel like there's something there, I just don't know what. If we were to manage to do that, then the only time I'd use pattern matching is basically to implement these things. Okay, so we're going to write isJust. First value needs to be a bool. So we're supplying this function f. That's the only thing we have in scope, just an f. So we have to supply it with things. We need to supply it with a boolean. Well, we're writing isJust, and so the first case is the nothing case. So that's false. It's not isJust if it's the nothing case. And then this one we've got an a to bool. We don't actually care what the a is though. We don't actually need that, so we can just write const true. It's always true. If it's this case, if it's the just case, it's always true. Easy. So is nothing, you can probably guess the implementation of this. It's not isJust. Or code duplication, you can say. Either one. I prefer this one. All good. Okay, cat maybes. Alright, now we're going to start dealing with list. Okay, this is going to get a little bit more interesting. Cool. So list. The encoded version has a B, which will be the nil case. This will be the nil. And this will be the cons case. And so the cons has an A, and then it's got an S list of A to B. Okay, this is interesting to me. So A, S list of A to B. What I would expect instead is to see this. Is this actually, does anyone who's good at Scott encoding, can anyone confirm that this is not actually a Scott encoding? Because to me, I would imagine us to see a B. I mean, let's look at this paper. The paper does compare, you know, church encoding and Scott encoding. And so the church encoding version, yeah, the Scott encoding version will have this nil, yep, in cons. The B would be the church encoding. Yeah, okay. That's okay. That's the exact difference, right? Yep, okay. Right, yep, so I see. Yep, here's the Scott encoding because of the recursive. Yeah, okay, cool. So, what I'm probably more familiar with is the church encoding version. So, yes, this is the church encoding version. You can see here it's got for all A, B, B, and the actual Scott encoding is, yes, it's got the recursive case here. Cool, okay. I was a bit confused there. Real good. Okay, so this is the Scott encoding version, so we've got the S list here. So let's have a go with this. Okay, cat maybes. So we've got, need to construct, oh, we have this S list, so let's, I don't know, should we deconstruct it? I guess so. I guess we're gonna have to deconstruct it anyway. Alright. Alright, so we need to return an S list of A. We need to return an S list of A. And what we have is an F. Here we go. Yep. Okay, so now we need to supply this F with a B. So what will this be? So we've got to return it with that, and then this thing here. Here we we go. Alright, so we've got an A, so we need to return, in the case that we have an empty list, so this will be the nil case, what should cat maybes do? It should return the empty list, which I don't think we've written, so let's construct an empty list. It will be, so we got a B, and we have an F prime. There we go, and we need to return a B, so we can just tuck in the B there. So here what we've done is just constructed the empty list, so we can call this nil. And the reason it's nil is because all it does is takes in the parameter that you supply for nil and returns that. Whoops, nil. Alright, so now we have the nil case handled. So this will be, so when we do cat maybes and you handle them and you get to the nil case, we'll just return nil. Now for the cons case, so cons will take in a maybe A, an S list of S maybe A, and return back an S list of A. So what can we do with the S maybe A in S list of S maybe A? What can we do with these two things? So we've got our maybe A and our list of maybe A. Okay, so we've got maybe A here. And so if it is nothing, let me decode this actually, so S maybe. There we go, so we've unwrapped it, so now we've got this thing here, we've got this F prime, which is the maybe. So if it is, so now we should be able to use that, and so let's say if it is nothing, so if it's got the nothing case, then what do? We just return L. We have to cat maybes of L, otherwise we do something else. Whoops. There we go. Otherwise we got something else. So what we have in scope is, so this is just recursive, so it's like if we hit a nothing, so if we hit the nothing case, then we just use the rest of it. So we just keep going cat maybes L. Otherwise, what do we do in this case? We've got our maybes of our list of maybes, and we have the just case. So we have our just, so we've got our, I'm getting confused here. We've got a maybe A. Why do we have a maybe A for this F prime? Oh, I didn't call the right thing. F prime, there we go. I was calling it on the list, and so that's why I was getting confused there. That was the nil case. Alright. F prime, so we're on the maybe. So now we're getting closer. Now we've got an A to a S list of A. So now we have to use this A to create an S list of A. So let's open this up a little bit. A. So now we've got a heap of things in scope. Heaps of things in scope. So we've got our L, which is our, the rest of the list that we're processing. So we're processing the head. This is the head. That's the tail. So the tail we've used here for cat maybes. We just got recursive call. For this one, we've got an A, and then we've got our L. And so we need to concatenate our A onto the result of doing it recursively. So let's go A. We don't have a cons yet either, so we should probably write cons. You think that fold map? Yeah, exactly. I mean, that makes it a little bit tricky because I'm implementing everything from scratch. Yeah, you're completely right there. Yeah, you would think that fold and map and everything would appear so that I could actually derive cat maybes in terms of fold and map. Yeah, maybe they purposely made it tricky. I don't know. It is a little bit backwards. I agree. So we've got our okay, so I've just implemented cons here as well. So here we implemented nil, here's cons. And you can just see the difference between nil and cons. Nil is just using the first one, cons is using the second one. So now I'm going to use cons A of cat maybes L, which I can replace with flip cons. So now what we're doing is just saying that in the case that we got nothing from the maybe, then we cat maybes, otherwise we do that. Which is that we cons on what the just value, so it's just. So we got a function, we got an A coming in, so we cons it on to the cat maybes. And there is a little bit of duplication here, the cat maybes L and the cat maybes L here. There should be some way to factor it out so that the F will return either ID or it will return cons. So let's have a go at that. So we want to do F of so say A, B, get rid of that, and we'll say we want to do that onto cat maybes L. I'm just trying to get rid of I'm just factoring out the code duplication that we see. So let's have a go at that. What we have is this case, that function. So this is the case of nil now, which is just we take an S list of A to an S list of A. That'll just be ID. In the nothing case, we just use ID on that. So we cat maybe, so this is the recursive call, so we just don't do anything to the recursive call. If we got something though, if we've got an A and a S list, well, we can just cons. So now you can see that we've factored out the duplication. Cat maybes L is here, and what we're doing is either in the nothing case we're using ID, which is just use the function, just use the recursive call. Otherwise, we cons on the thing that we got from just. So I like that. That's good. I will also lift these up to being actual definitions up here. So cons will look like, what will this look like? It'll be A, S list of A to S list of A. The nil will be S list of A. Cool, so that's lifted up. Looking good. Oh, duplicate. Cons already exists. Where's cons? Down below. Alright. So cons already exists, and so let's put in our implementation instead. Cool. There we go. We already wrote that in trying to solve an exercise, so that's good. Is there a nil? There is no nil. There's null, but that's not the same thing. Nope, there's no nil. Okay. Well, we've got nil and we've got cons now. Okay. To either. So I think that was, that was part one of list. I don't know why cat maybes was there. That's a weird place to put cat maybes up the top before we got to the rest of S list, but anyway. If anyone's done the Dice 1 FP course, this is, like, you might see some similarities between like what we're doing and like how we're implementing these functions, because we're implementing these in terms of basically in terms of their folds, in terms of the data types folds. Here we have though explicit recursion though, so it's not quite the fold, I guess. I mean, the fold will be the church encoding, like what we've said before. Anyway, S either F. Alright, so we need to return an either A, B. What we have in scope is this F thing. Let's use this F. We know that that's the only thing in scope, so we have to use it. A, B. Alright, so we have A to either A, B, B to either A, B. So what can we replace these two with? If we're going to this either type, remember either looks like this in Haskell. Either looks like that. Left or right. If we look at the type of left and the type of right, whoops. So these two constructors can be used as functions. These two constructors are just functions that we can supply in here. So notice how it goes A to either A, B. That is left. That's the same thing as left. So we can just say F is left, right. There we go. Now, the other way around. We have our either, and we want to create an S either. And so we've represented as a function, so let's supply a function. We got left or right functions. So see how this represents the left, that represents the right, because this one has an A and this one has a B. So the only data type, so with either, the only thing that's got a B is the right, the only thing that's got an A is the left. So this represents left, that represents right. So we're returning a C from this all. So we've got underscore to do, that means to return a C, and look what we've got in scope. We've got an either AB, and we've got a function from A to C or B to C. So what we can do is case E of left A, run L, otherwise right, run the right case. There we go. So that compiles, and like I was saying before, is I like to not use pattern matching, and I like to use functions when possible, and it is possible for this case. So we can say, what do we want here? We want, whoops, here we go. That's what I want. Either left, right, free. There we go. So that's a different implementation, and I think it's a lot nicer than using pattern matching. Alright, is left is going to be similar to, I guess, is just, right? Let's just copy and paste the implementation. So copy and paste the, so we had is just, which will handle the right side. So this will be, so we've got two functions here. So this will be const true and that will be const false. And thanks for Haskell for giving me the error to say that false was wrong. So there we go. Thank you, Jaxby, for that follow. So S either F, and so this will be just copy and paste. Whoops, copy and paste, and flip these around, or you can just say not is left. Same thing. Cool. All right. Down to the only list now. We've done the maybe, either, pair exercises. I think the only one left is now list. It is strange for that cat maybes to be there. I mean, it was dealing with lists and maybes at once. I mean, maybe that's why they had it there, because there was maybe. But I feel like they should be right at the bottom, like combined together everything. But anyway, let's implement. Oh, whoops! I missed a couple here. So toList. Let's implement toList. So we've got slist a. No, let's call it f because it's a function, isn't it? So to do, we need to implement a function. We need to give back a list of a's. What we have in scope is our function. It's got b, which will be the nil case. This is the cons case, and then we need to return back b. So I'm going to instantiate this b to be a list of a's. So everywhere you see b down here, think of list of a's. So this will be the empty case, which will just be the empty list, of course. So f of empty list. Now we've got one more hole to implement, which will be a. Let's implement as a lambda a, and it's going to be this s list of a. Okay, now we've brought everything into scope. We return a list of a's. And what we have in scope is everything here. We actually will probably make use of this function down here, this recursive call. So what do we have? We won't use this f. What we have is an a, an s list of a, and we've got two lists. So I know that we have to, this is the cons case, right? So we've handled the empty case, this is the nil case, and this was the cons case. Remember, list has got two constructors, nil and cons. We're handling the two constructors here, so this is the nil, this is the cons. Cons will actually go to cons, right? Like that will be the, because we're constructing up a Haskell data type, the actual Haskell list from the from S list, and so the Haskell list has got this cons operator, this cons constructor. That's actually a constructor. That's actually a constructor. So we'll use this cons constructor. We're replacing this with the constructor. So a cons and toList L. Oh, thanks, Justin. Thanks for coming in. We're talking about Scott Encoding today, and we're practicing it. There's some exercises on Codewars. If you want to have a go at this yourself, you can look on Codewars. This is the Scott Encoding exercise. Getting through it. We'll probably be done in the next, I don't know, 20 minutes. So that is toList. Notice how we've got an explicit call. If this was church encoding, like we pointed out before, we wouldn't have to have this explicit call. And this is really the difference between Scott encoding and church encoding. Okay, all good, that compiles. So we've created a Haskell list from slist. Alright, so now we've got another list. We've got this L. We've got this list here. We're going to call it L, and we need to construct an S list from it. So S list takes the constructor takes an argument, and that argument is a function which takes in, what is it, a B, and then an S list. Sorry, takes in a B and then a function to B. Replacing that with to do. So I need to return. What do I need to return? So we've got this L's. So I'm getting a message quite a bit at work. I'm just worried that things are down because I'm SRE. Just quickly checking. No, everything's good. All right. Okay, so where were we? We've got the whole to do, which has got type B. We've got this B in scope. We've got this in scope. Well, we've got this L. Right. So what we're going to do is fold over the L. Let's do this. So like what we've, you probably notice a pattern that we've been doing, which is that, here we go, with the either case, we did this. With the, where is it, with the maybe case we did, where's maybe, here we go, we did this. So notice how we use the fold function, and we just wrap it up inside of this constructor. So that's, we always start off with the pattern matching version as well though, so let's go that, and then the Const version. I think I need parentheses around this, there we go. Okay, so we've got two holes. The first one will be the empty case, so we've got this empty case here that we've been passed in, which is B. And then we've got the other case, which is we need to return a B, and what we have in scope is these things. And so we need to replace cons with this. Hey, how's it going? We are implementing Scott encoding exercise from Codewars. So if you look on Codewars and you search for Scott encoding, you'll see this. And we're just having a go at implementing this. And so Scott encoding is the idea of encoding your data structures as functions instead of encoding them as, you know, usual Haskell sum types. So in Haskell we can write things like this. We can write data either A, B is left A or right A, right B. So we've got a syntax for writing these types. What you can do instead is actually encode them as functions. And so that's what we've got up here. We've got these things as functions. Maybe is encoded as a function here, which takes two, it's a function that takes two things. It takes in a B. So I mean, this is polymorphic as well. So it's a polymorphic function. So you've got a return type B. So this will be the nothing case and this will be the just case. So you can kind of decompose your data type into functions, into function arguments. Like each case is a function argument. And why that is useful is, well, I mean, it's useful for some performance optimizations, but also because in like things like Java, we don't have syntax for sum types, and so what we can do instead is encode everything using functions. And so this is either written using Java, same thing. How's it going, all the Russian people? I have no idea what any of you are saying, but or if you are real, because you are probably not. How's it going, everyone? One bit for every constructor you turn into a function. Thank you. All right. I don't know how to deal with the bot problem. I guess I'm sorry, chat. You'll get drowned out. We'll have to deal with it. Okay, so let's keep trying with this. Where I'm getting a little bit stuck. Where are we? We need to, right. F takes an A. We've got an A. So let's use the A there, and then what we need to do is supply an S list of A's. And what we have is, well, we've got our rest here. Let's call it R. And then we can say from list R. Just a recursive call. And can we replace that with the fold? I don't know if we will be able to. But let's have a go. BF. We'll say fold R. So I'm just trying to replace it with like what we did with maybe before, and like what we did with either. Just trying to replace it with that. So we've got folder. Is this gonna? Oh, here we go. Yeah, it's a problem. Yeah, we can't even do it because why not? We can't do it because why not? What's the problem here? We can't do it. Thanks Ludo for trying. Yeah, thanks for having a go. I'm getting links sent to me how to stop spam bots. Thank you. Thanks everyone. Alright, you could require verified email. Yeah. Alright, I think I'll enable that then. Thanks for the link. And thanks Ludo for trying to do things. That's good, thank you. Moderation, well, it looks like they basically died off anyway, so thanks for doing that, Ludo. Alright. Okay. I'm not sure if I can do this with a fold right, because it's not in church encoding, it's a Scott encoding, so I'm not sure if I can, but Russian troll machine having a go? I guess so, yeah. I blame Soding. He's another Twitch person that does Haskell sometimes, and I think he's Russian, so I blame him. It's got to be him. Oh, because fold right. That's why I'm... Okay, well, whatever. Okay, there's a fold right that isn't Prelude's fold right, so it's fold right that works on, you know, S list. So, yeah, thanks so much, Ludo. I think you did a good job there. Thank you. Alright, so I'm going to skip that because I don't think we can use fold right because there's fold right in scope, and so I'd have to import it and it'll just be a big mess. So I'm not going to worry about that. So ignore my screwing around with fold right there. I think maybe it's possible, I'm not sure. Okay, concat. We've got, oh, this is going to be good. We've got an S, we've got an F and a G in scope. We've got two functions in scope. This one's going to be good. Very funny, Justin, very funny. It's Putin at it again, yeah. Trying to foil this Haskell. Alright, so we're deconstructing two S lists, and we're going to construct up a new S list. Okay, and let's bring the stuff into scope. We've got a B and F, actually H. So we've already got two of them. Okay, so now we've got to return a B, and what we have in scope is all this stuff. Cool. So, concat. Does anybody remember the implementation we used for FP complete? Oh, sorry, not FP complete. Don't ignore FP complete. FP course. With the FP course, we did a concat implementation, which was really good. Does anybody remember the concat implementation from the FP course? So for the for the empty case, for the nil case, we have to return a B. Okay, well we've got a B over here, so let's just return that B. Oops, there we go. And for the B case, which is the cons case, haven't done the FP course yet, but I saw your video and reminded me that you really should. Okay, yeah. There is a, I mean, hopefully I won't give away an answer too much by doing this then. Actually, I will give away the answer. I'll have to give away the answer. There's a cool implementation for concat. If you're either running concat using folds, there's a really cool implementation, which you'll probably see in a second. So A, S list, B. So we need to replace this const case. So this is the const case with an implementation. Church encoding of a list is pretty cool for allowing a snock. Yep. There we go. Concat is, you got a list and you go for each of the elements in the list, you add the element onto the list. I think that's JavaScript. I think Tony's writing some JavaScript there. Okay, so we've got the FB. So for appending, hang on, no, this is I don't know if I've done this right, because if we're saying that so we've got F, so this is our first list, right? So our first list, we're saying in the empty case, so if the F is empty, I mean, you have to think about this as folds, right? So the first argument to F is the empty case, the nil case. So if nil, if we've got nil, if the first argument that we pass into concat is nil, then what do we return? What is concat? It equals x's, right? So if you concatenate nil with x's, you get back x's. So we need to make sure that that's what we're doing in this case. So with the first case nil, we need to return back, well, g, basically. We need to return back g. So can we do that? You know what we could do is not even deconstruct this g. Okay, how about that? Oh, we can't do that. Yeah, okay. We can't do that just because then we have an S list inside of an S list. So that doesn't make sense. Okay, so I think we're going in the right direction now. If we got the nil case, then what we do is we use the g, we use the the g, and we supply the same things to it. So we're just saying that if you hit the nil case for our f, then just use g. Otherwise, this will be the const case, and so we've got an element in our f. So what do? We have to, this will be the equivalent code down here, we have to take a cons a's, we have to say, well, recurse, right? Concat a's and x's. So see how we kind of moved this cons into a plus and we just recurse. And that's what we'll do, have to translate into this. So we'll just translate this Haskell code down here into our Scott encoded version. So we've got our underscore b takes an a and an s list of a and our s list of a. And what did we say we had to, oh, whoops, I put a plus plus there, I didn't mean that. We are implementing plus plus. I meant cons. So we're just taking this a, moving it over here, and then we're concatenating these two things. So what we should do is cons a onto something. So we need to put in, oh whoops, we've got unexpected type. Where have I made a mistake here? I've made a mistake somewhere. Oh, I need to return a B, and what do I have in scope? Something that returns a B, no cons there. I don't want cons there because I want to use, I want to use the, what do I want to use? I want to use the, what have I done? I've got B in scope and H in scope. That's what I want to use. I want to use H, don't I? Is that right? I want to use H? I think I want to use H. Yeah. Oh, HAL. Thank you. Yes, that's exactly what I want to do. HAL, which is the same as H, right? But I've got no recursive call to concat though, so I don't want to use HAL. I want to do concat. Yeah, that's not right. That's not right. I do want to use concat. I wanted concat Why is concat should not be recursive here? And we've gotten lost there. Whoops. So you're saying this is the solution. Let's have a go then. Oh, you just substitute the nil case. No, I'm still lost. Well, what we can do is just test it out. Const. Alright, there's no instance of show. Okay, well, we'll just say tootless then. Yeah, we do need a recursive call. Because this will substitute the empty case, but then we'll just use the list. So in this case we'll just use the list. Yeah. So, all right, I'm not too confused. Okay, so in the const case, if we just use h, then that just means just use that case. Yeah. So it's not actually recursive because we do need to use concat because it's Scott encoded. Okay. So we need to substitute in here. So we need to say concat but that's a problem. That's exactly what I had before. That's it, right? That's the same thing as what you're saying. GZH, oh, sorry, C. Yeah, this is exactly what I've got. No, that's not the right answer because it doesn't recurse. We're only handling the case where we've got nil here, and then we're saying that the list is if this is the const case. Unless I flipped something there. Have I flipped it? No, I've got it right. I've got exactly what you've got. I'll even alpha rename it for you. Z, C, Z, C, whoops, C. Is that right? Yes, that's exactly what you've written. And yeah, that's exactly what I've got. Just alpha renamed. Yes, so this is not it because we have to have a recursive call. And this is tricky now. This is tricky. So we've got A, L, and our L will be our S list, so we can concat with our L. But then we've got an S list coming out of here, so we'll have to kind of like break that down as well. And that's where it's getting tricky. Maybe that's what we'll have to do. Maybe we'll have to deconstruct it. Yeah, concat is folder. Okay, folder flip folder cons. So it's folder. Hang on, flip folder cons. Hang on. Plus plus is flip folder. Right, that is, yes, so that's plus plus, which is concat. That's the same thing, right? Yeah, that's plus plus, which is concat. That's the same. So I got lost with the folder. Oh, concat. Oh, okay. Yeah, so this concat is plus plus. Yeah, this concat is not what concat usually is, I guess. Yeah, exactly. Yeah, it's not this concat. Yep. Yeah, sorry, that is a bit confusing because the built-in Haskell concat looks like this. The concat that we're doing is plus plus. Yeah, so you could substitute that with plus plus. So you're saying yes, flip folder cons is the same as concat. Oh, that's no problem, Ludo. I helped Ludo. Ludo tried. Yeah, he had some Haskell problems on Windows. Yeah, and so we got past that, which is good. Well, we got past most of it. Doc test we couldn't get installed for some reason. We tried stack, and stack of course didn't work. Hopefully you can still do your assignment without doc test. I don't know if you can, but hopefully. Windows, yeah, who needs that? Yes, so what are we going with? We go flip folder cons is concat, is plus plus. And that's what we're trying to implement. And so, yes, we got close to there. We've gotten stuck on it. I mean, it's because it's Scott encoded. The issue is, right, it's Scott encoded rather than church encoded. So we do have to have we have to insert like a recursive call into our cons. And that's what we've gotten stuck at. So I guess what I'm going to try and do, we'll go back to this. We need to return a B. What we have in scope is all of this. Our L, what is going to be our L? So this is going to be the rest of the list. And our A is going to be the head. What we need to do is say A is going to be const onto a concat call with this L and then G. Each node in the list is its own lambda complete with its own Z, C bindings. That's correct. That's exactly it. So that is the issue, okay? I mean, I think this is actually like one of the criticisms. Oh, I think this exact function concat is one of like the criticisms or one of the tricky things with Scott encoding. I think this is explicitly here to point out one of the problems with Scott encoding. I don't know if I should keep moving on and come back to it, or yeah, maybe we should keep moving on and come back to it. I think zip might be a problem as well, though. Actually, maybe that'll be easier. I'm kind of conflicted whether we should move on or keep trying this. We've gotten a bit stuck with the multiple things. Maybe someone could help out. Yeah, let's move on, and if someone can help it, we'll leave that to last. Let's go on to some more easy ones. These will be super simple. They're basically what we've done before. So null. So remember how we did is right and is left. Well, null is basically is empty, is nil. So this will be this will be true, and const false. Const false. So we're doing two const because we take two arguments, but it's always going to be false because it's const. Alright, and we'll call that F. Length of a list, if it's nil, it's 0. Otherwise, it is, well, we don't actually care about that. We do need that list, so then we say it's length of L plus 1. Sorry, I'm just going through this really quick. I think we've had enough practice with it so that we can go through this pretty quick. I think everyone gets the idea. Okay, so now we need to construct up an S list. Alright, you've come up with an implementation for me, I'll try it out. Okay, so to do, okay. Let me finish off this and then we'll take your implementation, try it out. So we've got our H function and we need to make a new function. Why do we need to make a new function? Need to create an, to do is a whole that takes a okay. I'm confused by this. Why are we constructing? Oh, this will be the nil case, right? Keep it consistent. There we go. All right. So I'm getting lost with my own stuff now. So there we go. We got C, which is the cons. We're implementing map. So what we have to do is replace in G, we're going to replace cons with, sorry, we're going to replace nil with nil, and we're going to replace cons with something slightly different. We're going to take an A and an L. And so we're going to replace the cons with cons that runs F over A, and then cons it on with an L, right? Is that right? Except, oh, actually that L we're going to have to map. We're getting somewhere. Oh, C. Okay, there we go. We're getting somewhere. Okay, so we need to replace it with C. I spelled out cons, but C is what we actually want to use. C is the replacement for cons that we're going to be given in this list. And so we need to replace that with, then we go map F over L. Is that right? Oh, okay, that was a bit tricky. We got there. So we're going to get, this is going to be, I think, similar to what we had before. The map is going to be a bit tricky because of the, like what we had with concat. We had two lists and we need to create a new list. And so I'll leave that one until a little bit later. And here what we're going to do is derive fold L and derive fold right and derive take. So fold L is going to have an F, B, and L list. What can we use here to get back a B? Well, we have to use, I mean, we could just return B, but that's not the right implementation for fold L, so we have to use this F. Is that right? No, we have to use this, we have to use F, but we have to use it in this G. So we have to go G, 0 cons, nil cons. Hang on. What did I do there? Oh, right, so G takes the, yeah, it takes the nil, so the nil will be B. Right, okay. And then we have an A. Thank you for the follow, Twangle. Thanks for the follow. So to do is A, S list of A and B. So we have to make sure this is a fold left, not a fold right. That's going to be another tricky thing. Yeah, that's going to be another tricky thing. That's going to be something that's going to confuse the crap out of me in a minute. So we have a function from A, L to something. It's going to be a B. I thought this was going to be a pretty quick Scott Encoding. I thought I was going to breeze through this, but you know, they put a couple of tricky ones in here. This is why, I mean, it's called it's it's you know, it's a highly rated. I mean, I don't want to explain the ranking system, but yeah, it's like it's basically as good as tricky as you can get on this website. So I was a bit overconfident maybe. So to do is B, we have to return a B, and what we have in scope is heaps of different things. Which ones do we want? We're using G, so we don't want that, we want F, right? But we need to come up with an accumulator. Here we go, so, okay. Now this is where I'm getting tricky, where I'm getting super confused. Between fold left, how to implement fold left using fold right. It's a common thing. Like fold right is like you know, kind of like the essence of a list, and so you can implement fold left using fold right. I just never remember. So here we go. Menial names. Okay, yeah. I should replace Sonic with the Haskell logo in my game. Yeah, we'll make a Haskell platformer. Accumulators of functions built up via repeated function application. There's no explicit lambda. Okay, well, I mean, repeated function application to build up an accumulator, well, to build up a function is, you know, super easy, since that's exactly what we're from Scott Encoding. I think I will have to replace the Haskell logo in Sonic. Let's have a go at fold Riot. Yeah, let's have a go at fold Riot. I think that might be easier. If we have a go at fold Riot, we can derive fold L in the same way. Like, so we could actually probably skip this one. I mean, this one's really gonna confuse the crap out of me, so. Alright, so let's have a go at fold right. This should be easier. This should be easier. Because the Scott encoding is more like fold right than what it is fold left, so hopefully this will be easier. What we have in scope is something that needs to return a B. We've got heaps of different values in scope. So this is the cons case, and so if we've got a cons, then we need to run our function with A and then something here. So we've got our function from A to B to B. We need to return a B, so I've just put in a hole here. So now I just need to fill this in with the accumulator. And what do we have as the accumulator? Well, we don't have an accumulator, but what we do have is a recursive application. So we can say fold R, F, B, L. Is that right? There we go. I think that is fold right. Type so fold right with, I mean, I'm just going to make sure that it gives us even the right answer. So fold right with cons 1, cons 2, nil. There we go. So it does actually, you know, go recursive, so it's fine. That actually works. There we go. Okay, so it is doing something. Now, is it actually a fold right? Yeah, that's not a good example. What's a good way to test that this is a fold right? It would be to replace cons with cons and 0 with nil, and that would be identity. So we say toList. There we go. That is fold right. Cool. All right, I'm happy with that. And so we can say basically what we've done here. So we can say fold left. Fold left is fold right with ID. Sorry, with ID as the initial element, and what do they do here? They just compose together the functions, right? Compose, yeah. What's the problem here? Fold right. All right, because you have to give it the there's a list and then B. There we go. Okay, now it's basically function composition. I mean, we're basically porting this code straight over. It makes it super easy. So that is. So we need to return a B. What we have in scope is a lot of different things. We need to use this B. I'm basically going to port over this though. I think we can just copy and paste it over. Okay, there we go. So that's fold left, and let's just make sure that works. Fold left is flip cons. There we go. So I don't know, fold left, flip cons nil is the way to implement reverse, and so that's what we just did using fold left. So this is definitely fold left as well. So we've got that. All right, so now we're down to three last things. So we've got take, zip, and concat. We're down to 3 last exercises. So we've got n for our take. I'm going to go in the order of, we're going to finish off take, we're going to go back to concat, and then go to zip. So in the case that we try and take from nil, we get back nil. In the case that we try and take from cons, well, we have to look at n. Okay. So if n greater than 0, then we are going to actually cons it on, otherwise we are going to, what are we going to do? We're going to just return back nil. Is that right? We'll just return back nil. Otherwise, if n is greater than 1, then we take 1 from something else, and we cons on our c. So we use c with what? I know that we're going to use c, so let's just do this. Actually, well, it'll be, instead of nil, it'll be z, I think. Alright. We're still going wrong somewhere. Where are we going wrong? This is pretty tricky, this one. So we need to return an S list of A, and what we have is, we've got C, which is an S list of A, Z, which is an A. Okay, oh, this is the oh, I've confused things up here. So this is A, and that is L. Okay. I've confused by using variable names there. So A, I thought this represented Z, and that represented the nil, and that represented the cons, but it's not. That's not right. We've already got that there. So we've got A and L. So what we do is we say if n is greater than 1, then we go A, the cons A onto take and take 1 from L. Is that right? Otherwise we return nil. Is that right? Come on. That might be right. Let's take 2 from that. Okay, we got it. Okay, take. That confused the crap out of me for a minute. We got it. Alright. We're down to concat and we're down to zip. And then we'll submit this and I'll end the stream because I'm done with this and I need to get some work done. Concat. Isn't that backwards? Oh, it is backwards because I wrote reverse in here. It's purposely backwards, believe me. Yeah, there we go. I got rid of the reverse. Cool. Thanks for pointing that out, though. That could have been a problem. So thanks for pointing that out. It's my own problem that I created. I put in a reverse function in there. Cool. All right. So concat. Let's see if we can do this time. Oh. We're going to. What are we going to do? I'm thinking that maybe constructing an S list here was maybe a bad idea. We want to use. Maybe that was the problem. Maybe this is more the direction we need to go in. I think we're starting in a better place now. I think the problem is that I saw S list here, and then S list here, and I deconstructed, then I reconstructed. And so then it was getting confusing where I'd have to run an S list. And I didn't have to if I wrote it like this instead. If instead of me constructing an S list here, I could have I'm just going to be able to use it. I think this will put us in a much better position. So we have our A and our L. So this is the cons case, right? So we say cons A onto something. This should compile now like it didn't before because we had too many S lists in scope. Well, not in scope. We were constructing an S list where we didn't have to. That was the problem. So now we've got a to do here. We need to give it an S list. What do we do? Well, we concat. What do we concat? Our A and our B. So we concat L onto, and this G here I'll get rid of as well. G. There we go. That compiles. I think that's right as well. Concat. Sure, I can post this to a gist. Sure. No, it didn't work. It didn't work. Why didn't that work? Oh, of course it didn't work, because you have to replace nil. Yeah, the one thing that I actually just re-implemented, like ID. Or const. I implemented const because G. But this is where we need to use G. This is the only, like, when we get to the empty, when we get concat, like I wrote before. Concat that equals that. So when you have the empty list, you give back the second thing. So that's what we didn't do. There we go. So I think now if I run concat, there we go. Awesome. We have concat. Deleting the code and retrying from scratch was a good idea. And luckily we delayed it and we kind of left it to last. Okay, now we're down to zip. I'm a little, I don't know if, like, I don't know if people, this is Codewars, I'm going to submit it to Codewars. I don't know if anyone has a problem with me submitting that to a gist or not. I'll probably do it anyway because I don't really care. Yeah, I'll just do it anyway, who cares. It might be against the rules, I don't know. They can ban me if they want. Alright, let's see if we can do zip. Zip might be the one that is a trick. I remember, like, Scott Encoding has, like, there's a couple of, there's some tricky cases with Scott Encoding, so maybe this is one of them. Oh, I don't care if it's against the rules. It's best, like, if you have any use for it, then I'll submit it. It doesn't. I'll put it onto a gist. I don't care. All right. So how do we do this? We want to replace each. So if it's nil, it's nil. If it's cons, if it is cons, then what do? We want to use G, and if G is also nil, then it's nil. So basically we go to, like, the length of each one. Like, so if either, so we've got two lists. If either one is nil, we return nil. Easy case. In case that they're both cons, now we have this in scope, right? We have B and L prime in scope. How about that? We'll say M. There we go. So we've got L and M in scope. We've got A and B in scope. I think this is actually going to be easy now. So we need to go say it is, we're going to cons. And what was our S pair? I'll leave that to later. And then we'll say zip on the tail. So L and M. Okay, we've got one last hole, which is just to create an S pair. That's super easy. We can create an S pair. So S pair. How do we construct an S pair again? We have a function H. Okay, and so we have to give H an A and a B, and we have that. We have an A and a B. Wow, there we go. Zip, done. Alright, let's try out zip as well. So we had concat, let's try it out with, oh, let's keep the two list. Zip. Okay, now it can't show pairs. It can't show pairs. So what can we do? Oh, we can say fmap that with, is it two tuple or two pair? From pair. No. Two pair. There we go. Is that right? That's right, I think. Let's make it more clear that it's correct. 1 with 3, 2 with 4. There we go. We done it. That is Scott Encoding. In case you didn't know Scott Encoding, now you know Scott Encoding. And I really know Scott Encoding. That was super intense. Okay, so yes, so that's Scott Encoding. There's a few tricky parts in there, but we've got it. And all of this, I think, all of this can be translated into Java. So have a go at that. If you know Java, take this code. I'm going to put this on as a gist. Let me. I don't know if I'm even logged in on GitHub on this computer here. Let me see. Oh, okay. You want me to click this link to pattern matching? Okay. Let me see. Alright, what are you saying? You're saying I hate pattern matching, and oh, look, you've written patterns for me. Using the pattern syntax, pattern synonyms. So view patterns, what's the difference between a view pattern and a pattern synonym? I know, because I hate pattern matching, I don't use them. So pattern synonyms, I know, looks like that's a pattern synonym, right? What's a view pattern? A view pattern is where you can do like a pipe and then a pattern, right? I don't think you're actually using view pattern in here, are you? You're gonna have a go at a Scala implementation? Awesome, cool. I'd like to see that. So what you're doing here is snil, you're converting it over to, oh okay, so because the pattern matching is based on maybes. So I guess in this you wouldn't have totality checking either, you wouldn't have like exhaustiveness checking, would you? So when you combine them together and you've got this, if you missed the cons, it would not say that you've missed the cons. That's correct, right? Yeah, that's pretty cool. I like that. Yeah, it does mean that you... Oh, there's the complete pragma. Okay. Okay. Yeah, I like that. I mean, that's... I really don't really like pattern synonyms. It seems to me like you could just use these as functions, and I mean you can compose them together. But I mean it does have like what you're pointing at here is the complete pragma, the totality checking, which I think is cool. Yeah, that's giving me some ideas. I'll think about that. Okay, so am I logged in over here? Oh, I am. Cool. All right, let me post this. And then actually let's make sure, right? Let's do something. Let's actually cause this is, a little framework that you can do to test it. So let me attempt. What's the problem? Ambiguous nil. Okay, so they've implemented their own nil. So I'm gonna rename nil to nil prime. It kind of sucks that they have a nil and they didn't give it to me, but okay. Nil prime. I don't stream with a tiny cramped monitor size. I actually have two 23-inch monitors, so it's not actually a problem for me. It's just I only stream from a little window just to make sure that everyone can view it and it's legible. I hate going to Twitch streams. Like I watched a couple of programming Twitch streams and half of them it's like I can't read the text, and so I purposely keep a... I think everyone can read this text, even though it annoys the crap out of some people. At least you can read it. So there's no... Can we use to petition? Error call petition. Where's petition? I didn't see petition. Huh. We missed one. Okay. Luckily, yeah. Yeah, I'm just trying to make it readable. To me, it's like, it's just tiny on the screen. Like it's normal, probably normal to you. Yeah. All right. Let's write partition. Partition. This one might be interesting. Let's write partition. So, I don't know how we missed this one, but anyway. slist of f. And we need to return an S pair, so let's construct an S pair. Do we want to construct an S pair here, or do we want to, like, which one do we want to deconstruct on? I'm guessing, where do we want to do this? Yeah, I'm gonna go S pair here. I'm just thinking, like, where do we want to actually, like, do the folding, and I'm guessing we want to probably, like, do the folding primarily around this S pair. We'll make basically two things. So pair needs, this G will need we'll need two S lists, and that's what we're going to do. So we're going to basically partition. I'm gonna do this. I'm probably gonna cheat. I want to do this quickly, so I'm just gonna write two functions. I'm gonna write why is my computer going so slow all of a sudden? Maybe it's because I've GitHub open or something. Maybe this. You think I should uncons first? Do you think so? Okay, let's go. I'll take your advice. Let's do that. All right, pair goes on the inside. Sure. I was conflicted on that, so I'll listen to you. So. maybe that cat spew's gotten to my computer. So, you're saying that this will be better. Alright, let's give it a go. So now we've got an either and we've got our list. Actually, I think you're right. No, that's yeah, pair goes in. This is way better. No, this is really good. Yeah, this is way better. You can see because I've got this A now, which is so this A, whereas A is an either. So now what I can do is I've got this S either. Let me deconstruct that. Yeah, this is way better because now I've got this either. So now I've got this G in scope. So I've got either like if it's left or if it's right. So if it's left, I'm going to cons it onto the right hand side. Otherwise, I'm going to cons it onto the left hand side. Yeah, exactly. I'd have to do a filter, which I was going to do. I was actually going to do a cat maybes and write a function that converted. Yeah, but yes, that would be not as good as this. Yeah. I mean, I didn't really care about the efficiency either. So I mean, if I cared about efficiency, this is 100% better. But this is, I think this will actually make it a little bit easier because now I've got this function. I've got L, which is our list, which will be a consing or deconstructing further. So we'll partition that. Partition our L. So that's our recursive case, and so now we say, what did we say? We say we've got our P, which is our pair. So we need to give it two lists. Like, sorry, we have to give it a function that takes two lists to a C, so I could just do this actually. But I have to deconstruct it. Yeah, okay. Sorry, I missed that. We have a constructor in there, so then, yeah, that's a bit better. There we go. So now we've got this. So now we've got heaps of things in scope. We've got our A, which is our list of A's. We've got our B's, which is our list of B's, and then we've got our. We need to return an S pair, but we've got everything. We've got basically everything that we need. So our G here will be our like our fold over either. So we can say that if it's left, then add it onto the cons it onto the left. It's getting deeply nested, it's not very nice, but is it still type checking? It is. Okay, so we still need to return a pair in each one. So we've got our A, which we can cons onto our list of A's over here. So we can cons A onto, sorry, cons C onto A. And then over here we can cons D onto B. And that needs to be a pair though, so we need to make that into a pair. So we need to say S pair give it a cons, this will be the left hand side, and then we need to say, what's the B? Did I get that one right? And then I need to say, I don't know if this actually might be able to factor this out. Yeah, I might be able to factor this out in a different way. I think I'm constructing pair in the wrong way, in the wrong place, sorry. Let's get this compiling, and then we'll see if we can make it a little bit better. And then that will be, well, whoops, A. What did I screw up there? well, parentheses, I think. Oh, there we go. Okay. Alright, I thought I was going the right direction. Okay. And I was. Okay, so I think see, I've got a little bit of, oh, I guess it's not that bad. But I am constructing the S pair twice, so I can either, what I can either do is leave it how it is, or I can make it so that I construct the S pair once, and then I can fold over the either, and say either it's A or it's ID. Like basically either it's cons or it's ID, like what I had before. I don't know, my Emacs is frozen though, so I don't know what's... Maybe that's a sign I should start not doing this. Yeah, it's completely frozen. Takes a while for Emacs to start off for some reason. Okay, Scott.hs. Oh, not Scotty. I've been trying out Scotty on Eda, so I'm used to typing Scotty. Okay, let's refactor this very slightly, and then I'll stop it there, and I'll submit the answer. Actually, while I am refactoring, I'm going to submit this answer. Let me submit this and see if it even works. If it works, then I'm happy. Cool, it works. Alright, so I'm going to try and refactor it very slightly, very quickly, and we'll end it there. So here, we'll say S pair. So H will take either, so it'll be cons. Actually, let me put in a hole here. Hey, I'm getting a bit lost, so let's do this. All right. Whoops. Okay, so it needs to return an S list there and an S list there. So this will be the lefts and that'll be the rights. Okay, cool. And what we have in scope is the lefts and the rights, because we've already got A, which is an S list, and B, so we've already got that. So what we need to do is say that if G, yes, so we need to fold on G and say that if G is a left, then we flip cons onto B. Otherwise it's just B. But we can actually just, instead of flipping it, we can just say, apply both these to B, so the cons. There we go. That should be it, shouldn't it? Oh, that's const. Flip const. Or const ID. Because in the right case, we don't actually care, so. Come on, and we're getting closer. That needs to be A. It does need to be A, exactly. Thank you, Haskell. And G const ID cons B. There we go, that's a bit cleaner. Cool, I like that refactoring. It's still a bit of a mess, but it'll do. Yeah, still a bit of a mess, but whatever. Alright, something like that. Cool. I will submit this as a gist. I'll submit this as a thing to Codewars. And I'll submit it as a gist. Oh, what have I done now? Did I make a typo somewhere? Oh, somehow I deleted fold L. How did I delete fold L? Maybe it was when Emacs froze. Somehow, yeah, fold L got deleted. Oh, that's annoying. Hopefully it didn't delete too much more than fold L. Oh, that's so annoying. This is why you should commit everything every second. Ah, that's super annoying. Which is fold Riot. what's my problem here? Thought I got that. Oh, I flipped the. Is that what I flipped? And everything else is right. Isn't it? No, it's not. Ah, I see. BG. I see. No, that actually is G. There we go. There we go. Alright. Got a bit confused there. There we go. Alright. Hopefully I didn't delete more. Hopefully I didn't delete everything. Okay. Okay. Where's my gist? There we go. Create gist. Submit. I'm done. Alright. You've ranked up. Okay, cool. We've done it. That's the solution on how to Scott encode maybe either list and pair. Alright. Oh, I'm worn out after doing that. Okay, time for me to actually do some real work for work. So, thanks everyone for coming in. Thanks for all your help, everyone. You know, actually I should have changed the title of that. I'm sorry that it still says Sonic 2. Yeah, I'm sorry about that. Next week we will do some Sonic 2, I think. I'm not going to do Codewars for a little while. That was intense. I'm happy that I did it. It was pretty cool. But that's it. Cool. So let me find someone else to host. Thanks for coming in, everyone. And thanks so much for your help. I don't think I would have been able to... It would have taken me a lot longer if I didn't have much help. Alright, who should we host? Repairing my WSL Ubuntu. I'm interested in WSL because like I do a bit of Nix, and so that is one way of getting it running on running Nix on Windows. Random projects in Rust. Could do that. My browser's not very zoomed in. It's just I stream with a small resolution on purpose so everyone can read it. Free advice. I don't know. Is it good advice? Twitch plays Conway's Game of Life. That's pretty cool. But instead we will... I guess we'll go Rust. I mean, that's... Yeah, we'll go Rust. That's the most interesting thing to me here. Alright. Cool. Thanks for everyone for coming in. I've got to do some real work. And so we're going to host this person. Actually, I'll rate them. Rate them? Is that the way to do it? Yeah, rate them. Thanks everyone for coming in. I'll upload this onto YouTube, even though half of it was not very interesting. But, you know, I'll upload it onto YouTube. It actually took like twice as long as what I thought it was going to take, which is interesting. But yeah, it was fun. It was a good stream. Thanks everyone for coming in. Thanks for all your help. Say hi to this person, Musean. And I don't know if you'll enjoy Rust, but I don't know. Try and enjoy Rust. All right, I'll see you next week. I'll do some more Sonic 2 next week. Cool. I'll catch you then.